Okay. Okay. This is the record of the first part of the lecture of 16 December. And today, first, we have to a little bit discuss if you have questions with the previous lecture, because we started the previous lecture and there we had we studied the questions connected with normal distributions, connection between how we can compute the mean value, the expectation, and the variance connected with normal distributions. Okay, if you haven't for the moment questions, then let me for the moment show you how with Excel we can compute some integrals that appear in the study of random variables with normal distribution. So we shall turn to the whiteboard. How you can see the quality of the picture? Is it satisfactory or not very good?
It is good now.
For the moment, it is good. Okay. Then let us clean the whiteboard and start with showing you what kind of integrals you can compute numerically with Excel. From yesterday lecture. We know that we had, okay, we start from here and probably can write up to this point. We studied the normal distribution with these two parameters mu and sigma, and we know that for given mu and sigma,
sorry, we cannot see. We cannot see. Okay, thank you.
Now is better. You can see.
Yes.
Okay. So we have 1 over square of 2 pi. Here we have sigma, and then here we have a to the power minus x minus mu squared. Here you can see divided by 2 sigma square. This was our probability density with mu and sigma. And for the special case when mu is 0, sigma is 1, we have the standard normal distribution with this probability density, that is 1 over square of 2 pi, and here we have a minus x squared divided by 2. So when we have to compute for given a, if you have a real positive number, can be positive, can be in any case any real number, and we want to compute probability, that our random variable, let us call this standard zeta, is the random variable with fixed mean value and variance. Sigma or sigma squared, this is the same, 0 and 1. And when we want to see what is probability x to be bigger than a. So we shall use Excel, and practically this shall be for given a, shall be given by our Excel program, but more precisely, this is the same integral of our probability density P0 of x dx, but instead of taking integral from minus infinity to plus infinity, this integral was 1, nothing to change. We took from a to infinity. Why from a to infinity? Because we need zeta bigger than a. And therefore, this approximately with Excel, now we shall see how we can compute. For example, we shall take a to be, for example, 1.3, a shall be 2, and we shall choose different values in order to calculate this quantity. Of course, this quantity can be connected with another quantity. Let me see here. I can write this last line. Can you see here?
Not so good.
Okay, then if you don't mind, I shall clean the fact that A is given. We shall not need this generic thing. Now we are working with standard normal distribution, that is 0, 1. So I shall continue here. Our next thing that we shall see numerically shall be, for example, if you need for your standard normal distribution to compute probability that, and this is to be drawn, that zeta is smaller than a. Of course, in this case, we have to take another integral. So we have to take integral from minus infinity up to a. Here you see well.
Yes.
Yes.
Is it okay? And we have again the same P0x dx. And this shall be, as you can imagine, since the sum of these two integrals is 1, this shall be 1 minus probability zeta to be bigger than a. So you shall see, if we know this result, then this shall be computed very easy. This is 1 minus p of a. And now I shall share the screen, and we shall show how we can compute with normal distribution. Of course, we have to put appropriate parameters. But let me first ask, do you have problems to use Excel? Can you use it in principle?
Just a little, very little.
Yes, I am also. The problem is if you can, how to say, use this program.
Yes.
Because there is most of our students, they have Microsoft Office, but otherwise you can use Open Office, that is free of any charge. Any guy can use, any person can use it. So let us now share the screen and try to see our practical attempt with Excel. I think for your future experience, use of Excel is something quite useful. And let us now open, let me see, where is my Excel? Microsoft Office, yes, this is Excel. So this is with any computer is coming this version that is not paid, but you can use in any case. For example, here I want to prove to find kind of a function. So what kind of function I am looking for? Normal distribution. You see this, probably you can see very small, but it is norm point dist, abbreviation of normal distribution. So here you see what I shall put. X corresponds to our A. And I have to put after this the mean value and the variation. Two parameters. We said that mean value is 0, standard deviation is 1, and cumulative means whether or not you shall compute one of these two variables, zeta smaller than A or zeta bigger than A. But let me first ask you, can you see my screen?
Yes.
Yes.
Okay, somebody has difficulty to see it? If you can see, then I put normal distribution. Now I have to put X. For example, let us put A 1 to be X to be 1. So we compute the integral. Mean we set is 0, deviation is 1. Cumulative, I need to put true or false. Let us put true. And you see the value. This is, this means, okay, you see the value? Probably I shall zoom my zoom. Let us put much bigger. Now you can see better?
Yes.
So this is one of the integrals. If instead of true, I write false, this means I compute the opposite integral. And you see, as I expected, before it was 0.8 something, now it's 0.2 something. Let us now compute bigger value. For example, let us put 6. What does it mean 6? This means that I integrate from 6. You know what does it means? A to the power, this is 10 to the power minus 9. So this is approximately 0. So false means that I integrate from 6 to plus infinity, because my Gaussian, the Gaussian function, is very small when x is big. So if for the moment I want to ask you if you can now you cannot see the whiteboard, or you can still see, because I think there are two things, the shared screen and the small rectangle that, can you see this small rectangle in the whiteboard here? Or this is very small?
We can see you.
Okay, and contemporary, you can see my screen?
We see you little in the lower part of the screen. And then there is the sharing.
Yes. If you try to unpin, when you go to pin and unpin, because I cannot do this, you cannot make the whiteboard bigger, if I understand.
Yeah,
I have to stop sharing.
Now I click on you and see you, but it's a bad quality. I think that if you stop sharing, maybe it's better.
Yes, let us stop sharing.
Yes, it's quite better. The quality of the...
Okay, so I said A equals 6. And we compute the normal distribution. That is our standard normal distribution. I put this indices 0 and 1. And then I put false. False in Excel. When I put this parameter false, then this means I compute this integral, not this integral. Why? If you remember our Gaussian function, if we try to make it for real, for all values of x real, the Gaussian function is like this, campana. So it is not very lucky. My picture should be even function, but mine is not very symmetric. But somehow you see, if you take, for example, A, very negative, and if we take this integral shall be very small. If I take A, like I take 6 here, integral from 6 to infinity gives me this small area under the graphic, and this is very small. That's why when you put false, you compute integral from a to infinity of p0x dx. And we saw that this integral is approximately 0. Our numerical Excel computation when a is 6 showed that this is 0 something, a minus 9. This means 10 to the power minus 9. 10 to the power minus 9 is something that we can say is approximately 0, very close to 0. But when we take a to be 1, then this integral was our probability zeta bigger than a was approximately 0.24. This was computed.
Excuse me, we can't see.
Now?
Yes, now yes.
Okay. So I would suggest you, for example, if you can use for the moment your Excel, do you have possibility to use in this somebody can use Excel, or you are not prepared? We can postpone for our next exercises that we decided during ricevimento. But somebody, if you can use Excel in the moment?
You mean right now?
Yes. Complicated.
Yes, a little bit.
Okay, then I shall do.
You want us to share the screen and use our Excel? Excuse me, I didn't understand.
No, not to share the screen. Only you can try. I shall put you some A, and you shall try to compute by yourself. Then we shall share my screen and we shall compare for everybody, because I don't think everybody can use Excel. Oh. If somebody can use.
We can try. I don't know if...
Of course, in the moment, I shall share the screen to show you in Excel what you need. If you're with Excel.
So, I'm sorry, we have to use Excel also during the exam?
If you need, yes, you can use.
Okay.
But if you prefer not to use, of course, you shall not use. I think Excel is something very quite useful.
Okay.
For your future work. Therefore, let us see first the experiment if you succeed to do this easy. And if it is not a problem, why not to include numerical stuff with Excel for our final discussion? This is one function in Excel that is needed.
Okay.
Okay, then I want to ask you to find this normal distribution function. So, as you can see, in Excel, there is possibility to look for a function. And if you haven't the function known, I should, for example, write here, if I am looking for normal distribution, and I am asking, and you see several normal distribution functions, and I am using the simplest one that is described below. What is the format? So I have to put x, the mean value, the standard deviation or variance, and then choose what kind of integral I'm using, from x to infinity or from minus infinity to x. False was from x to infinity. And I am clicking on this. And if somebody of you already succeeded to insert this, I would ask you to put...
Professor, excuse me.
Yes.
But in Italian is normalizza, because I cannot find normal
like norm.
I have just normalizza, and then there is norm, which I think is something different.
Asia, prova con distribuzione normale. Distrb.
Proviamo con i vostri suggerimenti. Sì? Qualcosa? Can you see something? Because I'm using, yes, Excel that is with English Microsoft.
Yes, I found it. Thank you. Sorry.
Yes, but what is exact command? Norm, point, dist, or something different?
I click on distribuzione normale, so it's distrib.
But what is the command? The command you are using? If you want, I can leave you to share your screen. Can you? So you can see the Italian version. Probably it is better.
Yes,
and I shall help you by, I shall stop sharing and shall propose you to, yes, now you can share your screen.
Do you see it?
I can see, yes.
I have this.
Distrib norm, versione italiana. Okay.
It's okay.
So you have to put some parameters inside the brackets.
Here.
What we shall put, for example, let us put 6 and enter to see what will happen. Now, without there is a comma or not? Let's see, probably some error will appear. Exactly, enter. What is giving some
Dice per la funzione sono stati immessi insufficienti argomenti.
Va bene, virgola, dopo 6, 0, 1, 0,1 e poi, ma non c'era qualche suggerimento quando lei ha trovato false or true? Era nella versione, qui dobbiamo mettere virgola, mettiamo true, proprio per vedere se esce qualcosa. Enter.
La formula contiene un errore, non si vuole digitare. La formula contiene un errore, dice.
Ah, allora,
Professore,
questo true
Asia.
bisogna scriverlo in italiano, forse.
Professore,
da me
Dà
funziona.
errore anche l'italiano.
a me c'è di me.
Funziona se è maiuscolo.
Ah.
E
Ecco,
ci sono i punti e virgola al posto delle virgole.
punto e virgola, ok. Ah, bravi. Nome, no. Adesso cliccando su nome, deve usare cliccando su nome, accanto c'è, che cosa è scritto? La formula contiene testo non riconosciuto.
Deve essere vero scritto in italiano, esatto.
Meno male, alla fine. Allora, nella stessa formula va sopra, al posto di 6 mette 1. Normal, perché qui integrale è più significativo. Proviamo. Ecco, 0,84. Quindi, quando ci serve di utilizzare Excel per calcolare, e stesso proviamo con altri parametri, per esempio, supponiamo che sigma non è 1, ma è, diciamo, mettiamo 2. No, sigma, quello...
Sigma, sì, sorry.
Terzo, sì, 2. Sì. Al variare, e mettiamo adesso mu 1. Deve ancora aumentare. Che cosa è successo? Ah, ecco. Adesso abbiamo qualcosa che dice che calcoliamo la metà dell'integrale totale. Vedete quanti esperimenti possiamo fare cambiando un mu? E adesso io vi chiedo, ma se noi sappiamo il risultato, ma non sappiamo mu, for example, how we can proceed if we can make many experiments, find this probability, and then try to ask how we can recover our mu, because we don't know, for example, in many cases, what is mu. We don't know what is sigma. So this is, how to say, a little bit more complicated. And that's why, if you don't mind, I shall turn to my lecture and try to explain you after this experiment, you know very well, if A is given, how to compute probability that the normal distribution is bigger than A. And you computed this with Excel with very high precision. Actually, what you computed, to be more precise, let us remind you that Excel is computing using standard tables this integral a to the power minus x squared divided by 2, 1 over square of 2 pi. This integral in general cannot be computed with simple tools as we did last time, integration by parts, and therefore this integral is computed numerically, and we can find the value with Excel. The same thing can be found if we change, as you can see in the normal distribution function, we can choose mu and sigma. And for any choice of mu and sigma, we have, of course, different results. So, in many cases, what we are doing with our statistical analysis is to have possibly collection of many data. So we make have, for example, if for example, we are doing with statistics for some virus infections. We are have, for example, statistics that says during this period, changing the period, what is the graphic of the infected people. So we have this statistical data. We make the conjecture that these statistical data are connected with some random variable, and we also conjecture that good approximation for our real process with statistical data is kind of normal distribution. Normal random variable with normal distribution with parameters mu and sigma. Somehow, what we can do is to make many examples. Say we take x1, x2, and so on. Big number of experiments, and in this sense, according to our theoretical approach, we assume that for each of these cases, we have independent random variables with the same parameters mu and sigma. And therefore, we have to solve the following inverse problem. From this data, from given data, all these experiments that gives us precise value of this random variable, we have to recover, for example, the mean value. For example, we can say that one good approximation of our, if we take some subsequence, we can find hypothetically value mu and some value of mu, and we want to check the following hypothesis. We want to see for given mu0 if our mu is mu0, yes or not. So we have two hypotheses. Hypothesis A is our mu is mu0. Hypothesis B is complementary. Mu is not mu. And we have to now to see how we can practically evaluate this hypothesis. This is so-called check of hypothesis evaluation. And we can give the idea how, at the beginning, statistically, we expect that our mu0 in some sense is given by the statistical mean value, x1 plus x2 plus xn divided by n. We expect that this is very close to mu0. We expect But this expectation is nothing else than only one hypothesis. This or this. So we have to see how practically we check our hypothesis, because if you prepare, for example, some statistical data, say this is normal distribution with mu equal something, who will trust you that this mu is exactly this one? You can refer to this question that I posed, how we can check if our mu is exactly mu0 using our statistical data. This is the problem. How we solve it, we shall see after a while, but the important thing in this appointment today is to understand that using our statistical data, we can have very precise, as we did with Excel, very precise calculation and say, this is really, according to our statistical data, mu is this guy with very big probability. And this is what we want to clarify after a while. But before starting to solve the problem, I want to ask if the problem, so-called inverse problem, how from your data you shall recover mu, can be reduced to check of one of these two hypotheses. So my question is if you understand what is the problem. Before starting to solve the problem, it is important to understand at least approximately the problem. We make hypothesis and we have to check that our mu is mu0. This is hypothesis for mu. You can make after this hypothesis on sigma. Again, we shall, we haven't time, but we can say that in the same way as we develop our strategy calculations for hypothesis A, we shall do similar thing for hypothesis of type sigma is some given value. For example, if you have concrete data, then we can make specific calculations at the end of our today discussion, and you can see, oh, with this statistical data, this hypothesis is not true. Or you can say, yes, with this statistical data, the hypothesis is true. And therefore, this is the question, the check of hypothesis. Let me stop for the moment to ask you if you have some questions, observations. This is very important practical question.
Professore.
Prego.
This is the method that they use in papers when we have at the end the results and there are the asterisk and they say that statistically is valid. So you use what we're going to do now. We may
exactly. This is of course what they have in mind, but what we shall show is one possible method, because there are different methods. Somehow it is important to take one method to understand what you are doing, and then you can see if they refer, oh, we apply method of X for verification. Then Mr. Google, you see the method and you see what is the difference. But if you understand one method, then the basis, this is the purpose of my appointment today, to show you how this can be done for the case of check of mu. So answer is yes, confirmation.
Thank you.
You're welcome. Okay. So always when we check this hypothesis, we have to define something that from the very beginning is very important. Appropriate a region where we shall evaluate our data. Therefore, let me explain you more precisely. In the check of hypothesis, before starting the method of the check, it is important that our check shall be finally based not only on these theoretical random variables, but on the concrete data. So, if we take concrete data, and with this data we compute x1 plus x2 plus xn over n. We know that this is the mean value of our statistical data. And if we take the difference between our mu0 that we have to check, then the important thing is to define case when the result is affirmative or hypothesis is confirmed or not confirmed. Therefore, for us, it is very important to know that our comparison shall be to say that our conjecture is not true. We need this difference in the mean value and mu0 is evaluated by some given constant C0 divided by square of n. I shall explain why this choice is important. So, to verify this or this, we have to define on the base of our data the set of this data xn such that this is fulfilled. This means when you have sufficiently large number
Sorry, we cannot see the upper part.
Now?
Yes, thank you.
Okay, sorry. So, in order to check the hypothesis, it is important also to make the following test. You take your mu0, and moreover, we have to define, because always you say our verification is based on this test, and you have to define your C0. So here, after a while, I shall explain why I have chosen here square of n, but it is important to define this constant C0. For our purpose, we shall put this, for example, let's take, to show the method we are applying, we take n sufficiently large and take some concrete value of C0. We know that we have to check this hypothesis, and therefore we have two possibilities. Or this is satisfied, and our statistical data are such that this is satisfied, and then we shall call this set of statistical data C. And if our statistical data satisfy this property, we shall say that what shall be the conclusion? We have two possible answers. Now we have, which are the parameters we have? mu0 is given, this is our hypothesis, C0 is given, and n is sufficiently large. We can take n sufficiently large. Then we are asking, this is true or this is not true? So, algorithm is the following. Finally, and we shall justify after a while, the solution of our inverse problem. If our statistical data the algorithm have the following answers. If our statistical data with sufficiently large n do not belong to C, therefore this inequality is not satisfied, but we have smaller than C0 over n, then we can say mu equal mu0 is okay. We confirm with big probability. Another possibility is if our statistical data xn belongs to C. And then we can see that our conclusion is mu is not mu0. We have to look for different mu0. So this is more or less the algorithm. And now I plan to justify this algorithm. Why? If we take now not statistical data, but random variables, normal distributions with mu sigma, we shall see that mu is very close to mu0. Practically, our hypothesis means something connected with the quantities that we studied, namely the expectation of our random variables. But I want to separate what are statistical data. Here we have statistical data, despite of the fact that we use the same x1, xn, and to justify our statistical test, we use the fact that we shall not check. This is assumption, you can say as axiom, that we have normal distributions. If this is true, okay, but we don't know. This check is not concerned if this is a normal distribution or not. This simply means that we know for sure that this is normal distribution with sigma given, and we are looking for mu. And we shall see after the small break that really, if now I replace statistical data with normal distribution, the calculation that I am showing shall show you that these answers are really very reasonable, and they are based on specific rigorous lemma, theorem or lemma as you prefer. But before the break, I wanted to clarify the question, show the answer, the algorithm, and then after the break, we shall justify our approach to show that it is really important to define C0. Once we know C0, we shall have the possibility to check our conjecture, hypothesis or conjecture, using this simple test, and especially defining this set capital C. Okay, if you don't mind, I shall stop the record and we shall make a small break. Yes, interrompi.